In this question, we have two narrow slits. We are given the width of each of the slits, that's A, and we are told that they are separated by 0.2 millimeters, so that's D, and illuminated by an electromagnetic wave from a laser. We are also given the separation between screen and slits. A viewing screen is located 10 meters from the slits. That's L. L is 10 meters. We are told that the first minimum in the interference pattern is 5 millimeters from the center of the central bright spot. The first minimum of the interference pattern is 5 millimeters from the center of the central bright spot. And precisely they are saying minimum in the interference pattern. Now the question is, what is the wavelength of the light used? So anyway, so we can visualize what's going on. This is an interference pattern due to two slits, not exactly the slits described in this question, but to give us an idea. This is our central maximum. This is the first minimum they are talking about. That's the central maximum. This is the first minimum. We can look at it either from this side or this side, since it's symmetric. Okay, now, they're asking us for the wavelength of the light used. So to do that, we need to use the equation for the position of the minima on the screen. The position of the minima is given by this expression of y sub n. 2n plus 1 over 2 lambda L over d. Again, it's 2n plus 1 over 2 lambda L over d. Now, for the first minimum, we need n equals 0. That corresponds to y sub 0 equal to lambda L over twice d. So we just solve this equation for lambda. Everything else we know. Y sub 0 is given to us, 5 millimeters here. L is given to us, it is 10 meters here. And the separation of the slits, D, is given 0.2 millimeters here. So we just work it out. Now one note here, 200 nanometers, that's not visible light. Okay, question B. What is the position of the first diffraction minimum for this setup? Now to find the diffraction minimum, we are going to use the expression for diffraction. Now the position of the minima is given by n lambda L over A. Now look at the difference between the expressions. This is for diffraction minima, this is for interference minima. They are quite different equations. The equation for interference maxima is going to look a lot like this one, not interference minima. Interference minima is not going to have the same expression or a similar expression to the diffraction minima. Okay, so the expression for diffraction minima is y sub n is equal to n lambda L over A, where A is the width of the slit, the width of the aperture, which is given in this case as 0.01 millimeters. Now that we know lambda from the previous question, we just solve for y sub 0. Now, they tell us the image below was obtained by a student when shining red laser light on a hair. Does the image show an interference or diffraction pattern? So we look at the image here. And notice here we have fringes. There is one here, very bright, that's the central maximum. And then there is another one, another one, another one, and so on. But notice how the one off the center has about this width, while the central one is about twice as big. The fact that the central maximum is twice as wide, that's sufficient to tell us that it is a diffraction pattern, because interference patterns, like you see here, the fringes are equal width. So it is a diffraction pattern. Now the next question is, can that image be used, if we have a scale, to find the diameter of the hair? Of course, all what we will have to do is measure the width of the fringes. Once we get the width of the fringes, we can, like what we did in the past, use the expression for the width of the fringes to find A. But A in this case is going to be the width or the diameter of the head.